Picture this, a jet so wide that if you tried to park it at the gate with its wings fully stretched out, it literally wouldn't fit. The Boeing 777X has a wingspan bigger than what most major airports in the world were ever built to handle. And yet, somehow, this airplane is going to land at those exact same airports every single day, tuck itself in, pull up to the gate like it's nothing. How? Because the moment those wheels touch the runway and the plane slows down, the tips of the wings literally fold up on a 350-ton machine while you're sitting inside drinking your coffee. Sounds insane, right? But that one almost ridiculous trick is one of the cleverest pieces of physics in modern commercial aviation. It's the reason the 777X can carry 426 passengers across an ocean, burn 20% less fuel than the plane it's replacing, and still roll up to the same gate as a regular 777. Without that folding trick, this airplane straight up wouldn't exist. Today we're going to break down exactly how it works, why Boeing had to invent it in the first place, and the physics behind why a longer wing is basically magic in disguise. Stick around, because by the end of this video, you're never going to look at airplane wings the same way again. So let's start with the problem, because to understand the trick, you have to understand why anyone needed a trick at all. In aviation, there's a number called aspect ratio. It's not glamorous. Engineers don't put it on posters, but it's one of the most important numbers in the entire science of flight. Aspect ratio basically describes how long and skinny a wing is compared to how wide it is. A short, stubby wing has a low aspect ratio. Think of a fighter jet. A long, thin wing has a high aspect ratio. Think of a glider or the wings of an albatross. And here's where physics gets beautiful. The longer and skinnier the wing, the more efficient it becomes at producing lift. Why? Because of a sneaky little troublemaker called induced drag. Here's what happens. When a wing creates lift, the high-pressure air underneath it doesn't just stay put. It tries to escape upward, around the wingtip into the low-pressure zone above the wing. And every time that air sneaks around the tip, it creates a swirling vortex of wasted energy. Those vortices, that's pure drag, pure penalty. The plane's engines are literally working harder just to drag those swirls through the sky. The longer your wing is, the smaller those tip vortices are compared to the total lift the wing is producing. In other words, a long wing leaks less, it cheats less, it's just plain better at being a wing. That's why gliders have those impossibly long, thin wings. That's why the U-2 spy plane looks the way it looks. And that's why Boeing engineers, when they sat down to design the 777X, knew exactly what they wanted: the longest, most efficient wing they could possibly bolt onto a passenger jet. And they did. Fully extended, the 777X has a wingspan of 71.75 meters. That's about 235 feet from tip to tip. It's longer than the wings of an Airbus A350, longer than the wings of any 777 that came before. It is, quite literally, one of the most aerodynamically efficient wings ever fitted to a commercial airliner. But here's where reality smacked physics in the face. If you're enjoying this so far, do me a quick favor and smash that like button. It really helps the channel. And if you're new here, hit subscribe so you don't miss the next deep dive. Now, back to the wing. Airports around the world are organized into categories by the International Civil Aviation Organization. These categories are based on wingspan. Code E, the category that handles most big wide bodies, in the 777, the A330, the 787, has a maximum wingspan limit of about 65 meters. That's the rule. Your taxiways are spaced for it, your gates are designed for it, your hangars are sized for it. The 777X's wing, 71.75 meters, about 7 meters too wide. 7 meters doesn't sound like much, but 7 meters is the difference between fitting through a doorway and crashing through the wall. If Boeing had built that wing without a solution, the 777X would have been bumped up into Code F territory, the same category as the Airbus A380 and the Boeing 747-8. And Code F airports are rare, expensive, limited. Suddenly, your shiny new airliner can only land at a handful of places worldwide. Airlines weren't going to buy that. Boeing knew it, so the engineering team had a choice: make the wing shorter, throw away all that beautiful aerodynamic efficiency, and build just another wide-body jet. Or get clever, really clever. They got clever. The solution is the folding wingtip. It sounds almost too simple. The last 3.5 meters or so on each side of the wing are designed to hinge upward when the plane is on the ground. When they're folded, the total wingspan drops from 71.75 meters down to 64.85 meters. Suddenly, you're back inside the Code E limit, back at normal gates, back at normal airports. The plane fits. And then when the pilots are ready to take off, they flip a switch in the cockpit. The wingtips swing back down, lock into place, and the wing becomes one continuous, smooth, ultra-efficient surface. About 20 seconds later, you've got a wing again. Comment below, did you have any idea that part of a Boeing's wing literally folds in half on the ground? Be honest. Now here's what's wild. The 777X is the first commercial aircraft in history to have a cockpit-controlled folding wingtip mechanism. Folding wings have existed before. The Navy has been folding wings on carrier-based fighters for decades because space on an aircraft carrier is precious. But on a passenger jet, carrying 400 paying customers across the Pacific, never been done. And the reason it had never been done is because the engineering challenge is brutal. Think about the forces at play here. When the wing is in flight, it's bending upward under enormous load. A fully loaded 777-9 takes off at a maximum weight of around 351,550 kilograms. That's roughly 775,000 pounds. A huge chunk of that weight is being held up by the wings flexing through the air. The tips of those wings are bending upward by several feet during normal cruise. They flex, they twist, they take massive stress. Now imagine you put a hinge in that wing. A door basically in the middle of a structure that's getting hammered by tons of aerodynamic load. How do you make sure that hinge doesn't fail? How do you make sure it doesn't flutter? How do you make sure it doesn't, say, accidentally fold up while you're at 35,000 feet? This is where the engineering gets gorgeous. The hinge isn't just a hinge, it's a structural locking mechanism with multiple redundant pins that physically drive into place when the wingtip is extended. Once those pins are in, the wing behaves as a single piece. The folding line essentially disappears. Structurally speaking, the aerodynamic loads pass through the joint as if it were solid metal. The wing itself is built primarily out of carbon fiber composite, same family of material as the Boeing 787 Dreamliner. Composites are incredible because they're light, they're strong, and they don't fatigue the way aluminum does. They allow Boeing to build a wing that's longer, more curved, and more efficient than anything they've made before without it weighing a ton. There's a switch on the overhead panel in the cockpit. Pilot reaches up, flips it. The actuators, basically heavy-duty hydraulic and electromechanical motors, start unfolding the tip. Within about 20 seconds, the wingtip is fully extended, locked, and confirmed. The pilots can see the status of the lock right there on the EICAS, the engine and warning display. They get clear iconography showing whether the tips are up, down, or somewhere in between. There's no taking off until those pins are locked. And on the way back, after landing, once the airplane slows down to about 50 knots on the runway, that's around 90 kilometers per hour, basically taxi speed, the wingtips automatically begin folding upward. The pilots don't even have to think about it. The system handles it. By the time you've reached the gate, the wings are tucked in, the airplane is Code E compliant, and you're being marshaled into your parking spot like any normal wide body. Now I want you to step back for a second and just appreciate the absurdity of what I just described. We're talking about a passenger jet with folding wings, where the folding mechanism is basically transparent to everyone on board. There's no jolt, no drama, just a smooth automated piece of choreography happening on a machine the size of a small building. But the wing is only half the story, because hanging underneath each of those wings is something almost as ridiculous. Mounted on the 777X is the GE9X engine, and this engine is officially the largest and most powerful commercial aircraft engine ever built. The fan at the front, the part you can see when you walk past it at the airport, has a diameter of 134 inches. That's about 3.4 meters. To put that in perspective, the fan of the GE9X is wider than the entire fuselage of a Boeing 737. Let that sink in. The front of one of these engines is wider than an entire single-aisle airliner you've probably flown on. And during testing, this monster set a Guinness World Record for engine thrust. In November 2017, in a test cell in Peebles, Ohio, a GE9X produced 134,300 pounds of thrust. That broke a record that had been held since 2002 by the GE90, which had powered the original 787. In its certified in-service configuration, the GE9X is rated at up to 110,000 pounds of thrust per engine, 2 of them on the wing of a 777X. That's enough power to push a fully loaded 800,000-pound airplane down the runway and lift it gently into the sky. But here's the wild part. Even though it's physically larger than the GE90, the GE9X is rated at lower thrust than its predecessor. Why? Because it doesn't need more thrust. The 777X's wing is so efficient, so optimized, so long, so aerodynamically clean, that the airplane just doesn't require as much brute force to fly. The wing does more of the work, so the engine can do less of it. That's a 10% improvement in fuel burn compared to the older GE90. Thousands of metric tons of fuel saved per airplane per year, less CO2. quieter takeoffs, a 40% smaller noise footprint than the airplane it's replacing. That's the elegance of good engineering, by the way. You don't always solve problems by making things bigger or more powerful. Sometimes you solve them by being smarter. The 777X is smarter. If this is blowing your mind, hit that subscribe button. I make videos like this all the time about the engineering and physics behind aviation, and I don't want you to miss the next one. Now here's the part where I have to be honest with you, because the 777X journey hasn't been smooth. The 777-9, that's the larger of the two main variants, with seating for 426 passengers and a range of more than 7,285 nautical miles. First flew on January 25th, 2020. The flight lasted just under 4 hours and ended at Boeing Field in Seattle. From the outside, everything looked great. Behind the scenes, the program was already running into turbulence. Literally and figuratively, there were issues with the GE9X engine itself. Stator vane components needed redesign. A compressor anomaly was discovered during pre-delivery tests in 2019. Each fix added months. Then COVID hit. Then the broader certification environment for Boeing tightened dramatically after the 737 MAX crashes, because regulators were no longer willing to accept the 777X as a simple derivative of the older 777. They wanted the whole airplane scrutinized. And then in August 2024, during a routine inspection following a test flight in Hawaii, Boeing engineers found something they really didn't want to find. A structural link, the part that connects the engine to the wing, called the thrust link, was damaged. They checked the rest of the test fleet. Cracks in the same spot on multiple aircraft. The entire 777X test program got grounded while engineers figured out what was happening. That setback pushed first deliveries even further out. As of October 2025, Boeing was telling customers that the first 777X wouldn't actually be handed over to an airline until 2027. Lufthansa, the launch customer, has been waiting years longer than originally promised. So has Emirates, which has the largest order for the type and has been openly frustrated about the delays. So is the 777X falling from the sky? No, quite the opposite. The airplane itself, when it flies beautifully. The folding wingtips work. The GE9X works. The carbon fiber wing works. The aerodynamics are everything Boeing said they would be. The problem has been industrial, certification, quality control, schedule, things that have nothing to do with whether the airplane is good, and everything to do with the fact that building a brand new commercial jet in 2026 is one of the hardest things humans have ever tried to do. Here's what I want you to take away from all this. The 777X exists because somebody, somewhere inside Boeing, looked at a brick wall, the rule that says no commercial jet can have a wingspan over 65 meters at most airports, and instead of accepting it, asked a different question. What if the wing didn't have to be that long all the time? What if we could have the long wing in the air, where physics rewards us for it, and a shorter wing on the ground, where the rules force us into a box? Out of that question came a folding wingtip, a piece of cleverness that lets a passenger jet break a rule it can't break while still obeying it, a trick that lets a wing be both 71.75 meters long and 64.85 meters long at the same time, depending on what physics is asking for at that moment. That's not just engineering, that's elegance. And honestly, that's why aviation never stops being amazing, because every time you think you've seen all the tricks, somebody invents a new one. Every time you think the rules are fixed, somebody finds the loophole. The Boeing 777X isn't just another wide-body jet. It's a 350-ton answer to a really hard physics problem, and it folds. So next time you see one of these things at the gate, and you will soon, take a look at the wingtips. They're going to be pointing up at the sky. Wait until the pilots are ready to push back. Watch them swing down. Watch them lock. And remember what's happening in that moment. Physics is being negotiated with. Rules are being respected and broken at the same time. A piece of cleverness that took 10 years to build is quietly doing its job, and most of the people on that airplane will never even notice. Which one of these facts surprised you the most? The folding tip? The engine wider than a 737? Drop it in the comments. I read all of them. And if this video gave you something new, drop a like, hit subscribe, and turn on the notification bell so you catch the next one. Because trust me, the world of aviation is full of tricks like this, and we are nowhere near done exploring them. Catch you in the next video.